So welcome to the lecture on quantum non-locality. This is going to be non-locality, and my name is Martin Plávala. So first of all, let me go through some of the important things, or what's the goal of this lecture? The goal of this lecture is to go through some recent results used in quantum information research. All right, so most of the things we'll be talking around here are like results from this century. From like this, not the last one, so 2000s and so on. And moreover, I'll try to structure the lecture in such a way that it will actually get you close to the actual research. So you'll somehow see how the research progressed and how it's done, and roughly where is the current cutting edge or of what we know. Of course, there are limitations to this because it would take a very long time to explain everything. So take this with a shovel of salt, but it will go way closer to the research than usual quantum information book should. Please do ask questions whenever you cannot read something, whenever something is not clear, whenever there is any issue, please ask me any questions, okay? There are no stupid questions. The only wrong thing is not to ask questions and not understand what's going on. Good. Does anybody have any idea about quantum non-locality? What do you think this is? So I would say that the point here, and the point of all of this lecture, is going to be that phenomena present in quantum theory, some of them don't have any classical analog. So there are some things in quantum theory that I just cannot explain to you in terms of classical physics or classical intuition. And that's what quantum non-locality is, stuff that quantum things do when there's two and more of them that we just cannot explain using normal intuition. So first of all, a simple example. This is one pen, and for all purposes, this is a classical object because it's big enough. This is another pen, and it's also a classical object. And we know that this one is yellow, and you know that this one is red. But if I put them together, you don't learn much more information about the two pens, except for maybe that they are like really identical. But this is not true in quantum theory. In quantum theory, we can have one particle, and we have roughly no idea what it's doing. We have another particle, we have roughly no idea what it's doing. We put them together, the information is perfect and precise. And this is one form of quantum non-locality, that you need two or more particles, you need to look at the whole system to actually know what the system is doing, what's going on. Can you imagine something like that? Yes?
Perhaps something like entanglement?
Yes, exactly.
Or other non-classical things. For example, if you argue that your pens would be quantum objects, then it could be normal to maybe toss one of them around the wall, and it might suddenly, well, act in a non-classical way, like a tunnel effect, for example.
Yes, exactly. And here the non-locality comes into the fact that we'll be looking at things which require two or more particles. So tunneling is, strictly speaking, not a non-local effect in this kind of thinking, because by non-locality will mean things more like entanglement and network effects. Very good. Let us make another thing. So can I have two volunteers? So please come here. But I need two of you, so one more, please. Okay, please come here. We'll play a simple game. You're going to face back to back to each other so you don't see each other. And what I want you to do is that when I clap my hands, you're going to raise one of your hands, okay? And I want you to always raise the same hand, both of you. Where the same means that if you raise left, you raise right, because it's like that you're standing back to back, so you have to flip it. But you can now talk and make up a strategy if you want.
Always the whole time the same with each clap. Oh, we two.
You two.
Yeah, I see, okay.
So, I mean, the obvious part would be we always raise the same hand.
Yeah.
So, if you clap, no matter what, we always raise left hand.
Or like we have a pattern that we follow each time.
But in that case, it would like depend on the time, and it would depend on when you clap something.
Yeah. Okay, so back to back.
Always
Let's try it.
the camera hand.
Yeah, you see it works. It always works. Always the same hand. Can you do always opposite?
Okay. Oh.
You can make a strategy if you want.
Okay, yeah. Do this, I do this.
Yes.
Oh yeah. Okay, I messed up here, sorry. Yeah, it doesn't always work.
Okay, good. So you see for rational agents, it should always work.
Yeah.
Can we add a third person? Yes, please come here. So usually in quantum information, we would refer to as Alice and Bob because we usually have two parties and they are Alice and Bob. So now, you please come here. You will be acting as an input. So you can either stand like this or you can raise your hands. Okay? If you stand like this, it's 0. If you raise your hands, it's 1. And so we'll have Alice input. And if it's 0, we want them to be correlated. If you don't raise your hand, we want them to be anti-correlated. Can you two make it work?
Together with him.
No.
That's kind of.
So we're not seeing his.
You will see his
I will
movements.
see this.
We both will.
No.
That's easy. That's easy. You always raise the camera hand, the left hand.
I see, and then you can
I'm
just do
just-
the other thing, and then you can decide whether or not
Yes.
you do the okay.
Because I'm seeing him.
Yeah, sure.
Could you remind me again? If he raises his hand, we should be correlated, right?
Yes,
No,
anti-correlated. Yes,
And if he doesn't raise his hand,
correlated.
correlated.
Okay,
Yeah,
and
easy.
I was the same.
Easy.
So if I knock, you set the input, and then I clap, and you raise your hands. Okay, let's try one more. Did it work? Okay, you can see we can still do it perfectly. One more person. One more volunteer, please. You now please go here, and what we'll now do is that there's going to be two inputs. So you're going to be Bob's input, and you're going to be Alice's input. Now, if it's both zeros, you're going to be correlated. If one of them is 1, you're going to be correlated, and if both are 1, you're going to be anti-correlated. Can you do it?
Like I will probably see him. You will.
Exactly.
Those two don't interact with each other. They
No,
just
but
do
they-
randomly.
They see each other.
Yeah, they do see each other, but they
It doesn't
do
matter.
whatever they want.
Yes.
So that's kind of harder. For me, I would just for this. It's not what we want to do, but the chance that it's the correlated one is higher, and then I would just aim for the correlated one just because of the Wahrscheinlichkeit, I'm sorry. Genau, exactly. And yeah, but it's not gonna be always correct. There's gonna be 1/4 where it's wrong. So that's not the way.
Yes.
I can only think of that out of my head right now.
Any better ideas? So if you don't know how to solve a problem, a good idea is to at least quantify it and somehow be able to say, how good is my solution? So for example, now we can say that we're going to give you points. And we're going to give you +1 point for each time that you are perfectly correct, and -1 point for each time that you are perfectly not correct.
I would always choose the correlated version then.
So in the 0,0 case, you would get +1 point. In the 0,1 case, you would get +1 point. In the 1,0 case, you would get...
+1 point,
And
and then
the-
-1 point, okay.
Yes, because you would be correlated instead of anti-correlated. Is it clear how this would work, what I'm doing here? So overall, you would get 2 points. Does anybody already see where I'm going with this? And in fact, this is the best strategy that you can do classically. The only way to improve this, that's known to people, is that if you would use quantum theory, so what we can do is that you would share a pair of entangled particles, you would measure them, and you raise your hand based on the outcome of measurement, at which point you can get 2 times square root of 2 points, which is roughly something like 2.8, blah, blah, blah. So quantum theory can, in this case, do something strictly better than classical theory can. Okay, thank you very much. You can sit down if you like. And in fact, what we are doing here is the CHSH Bell inequality. And measuring this kind of violation in a technically good enough way is what the 2022 Nobel Prize was for. So measuring this number. And essentially playing this game, but with quantum particles. And why is it non-local? Well, because we have Alice and Bob, and they are trying to somehow coordinate two actions between them and somehow try to beat what can be done classically and obtain some kind of classical advantage. And why is this practically interesting? Because, for example, you can do cryptography with this. Very well. So now that we have this rough idea out of the way, what we now need to discuss is the formalism of quantum information. Did any of you pass quantum information courses? Okay, so I'm sorry, you might be a bit bored today. Did any of you do a standard quantum mechanics course? So for the next hour, please somehow forget that you did that, and then I'll somehow explain to you how the two things are connected, okay? But don't be afraid that I'm calling something quantum theory that you will not recognize as quantum theory at first, or maybe only very vaguely. So in quantum information, we usually describe most of the settings, most of the things we do in terms of some kind of experiments. And does anybody work in experimental physics? Like actually in a lab? Very good. So how do you do experiments?
With a laser and the element on a table. What exactly you want to know? So if we do 2K experiments.
Yes, so roughly what are the steps?
Well, you need a source. Then you need to somehow encode your information from that source. Polarization, time bins, whatever different paths. When you set up something, you need to choose what
Yes.
you encode it on. So, for example, polarization, and then you need to, decide what you want to encode. So, for example, in BV84, you could choose polarization, and then you choose two orthogonal bases and switch randomly between them. And then you shoot those photons with the information to some other, where you do your measurement on them again in the end.
Yes, exactly. So there's three very distinct parts to this. The first one is that you prepare some kind of quantum state, or you prepare you have a source of quantum states, photons, electrons, whatever. Then you have some kind of transformation that does something to your system, and in the end you have a measurement. We can actually write this in a very efficient way, somewhat diagrammatically, that we have the preparations which prepare a state rho, we have a transformation phi, and in the end we have a measurement m. And this will give you somehow a probability distribution as a potential outcomes of your experiment. Now, and roughly every experiment can be described in this way, because you usually start the experiment by turning on the laser and preparing some states. Then you apply some transformations to make it more interesting, and then you measure. Of course, we can always somehow include the transformation into the preparation, or we can include the transformation into the measurement, at which point we're just applying it in Schrödinger or Heisenberg picture. Now, there's another thing that we can do. So imagine we have two different preparations. What can we then do? So I give you ways to prepare two different states of a particle or something. What can you then do with that? Yes?
Sometimes do the first one, sometimes do the second one.
Yes, exactly. You can just randomize between them. So then we have something we call convex structure in all of these things, which means that if we are given a number from 0 to 1, what we can do is that we can construct this p rho plus 1 minus p sigma, which must be also a preparation, where now the p is a probability of or somehow the bias of the coin we are tossing in order to decide whether we do this one or that one. We also p phi plus 1 minus p psi must be a transformation, and Pm plus 1 minus Pn must be also a measurement. Of course, this is assuming phi and psi are valid transformations and m and n are valid measurements. There's another important thing that we usually have in an experiment, and that's something that can be roughly referred to as tomographic completeness. What this just means is that if you have two different preparations, then there is some kind of measurement that can distinguish between the two preparations. Okay, so completeness, which just means that for all rho sigma such that rho is not equal to sigma, there exists a transformation and measurement such that this thing is not equal to that thing. Where at this point I am not putting the exact meaning what it means, this thing not being equal to that thing, but you can somehow understand what I mean by this notation, right? Now, of course, the same thing should hold for all pairs of transformations that are different. And the same should hold for all pairs of measurements. What does this tell us, this tomographic completeness? What's the meaning of this? Like the logical meaning, why do we want this?
To distinguish different states and different operations with them. So
Yes.
they form something, a complete system, so you have no options on the.
Yes, that's one way to look at it. Actually, there's two equivalent ways to look at it. One way is that we somehow want to make sure that we have ways of distinguishing two different systems always, at least in principle, at least in theory, and at least statistically. A second way is that we want to make sure that if we have two different preparations that always output the same state, or somehow if we have two different preparations but we change parameters of the preparations that do not affect the result of the preparation or the result of the experiment, then we always want those two things to be considered the same. So, you know, if your colleague is doing an experiment in a lab, then it should not, like the state he prepares should not depend on whether it rains or not. It is a parameter of the preparation. It could in principle affect the outcome of the experiment, but it should not, because we somehow consider weather somehow distinguished from our experiments in our labs, or well isolated from that. Very well. There's now two problems. So somehow you trust me that all I've written is reasonable, right? Okay. There's two problems with what I've wrote so far. The first one is that this doesn't tell you how to compose systems. So I always considered experiments where you prepare a single system, transform a single system, and then measure a single system. But non-locality should be about what happens when we have more than two systems, two or more systems, and this doesn't tell you how to compose systems. We have to put that in by hand, or somehow you cannot derive that from this. In fact, you cannot even derive quantum theory from this, because quantum theory is not the unique theory that would satisfy this type of reasonable operational axioms. And there was, for example, a long axiomatization program running from something like 2001 to early 2010s, when people were trying to take these type of assumptions and try to pile on more assumptions that would uniquely specify quantum theory as the unique theory with some kind of reasonable axioms. And there are several papers which find, and usually some assumptions, and then there's like one or two assumptions that are somehow very specific to make the proofs work. And this is one reason why people say that they don't understand quantum theory, because there's no good way to derive it. It's just, you can start writing reasonable assumptions, and then you realize that there's many theories, mathematically consistent theories, that would somehow satisfy all of your assumptions, but they're not realized in nature. And the one theory that we have in nature, quantum theory, is amongst them, but it's not somehow uniquely specified by these types of assumptions. Unless you, of course, start adding all of the assumptions that then are, say, a bit harder to justify. And in order to somehow motivate that, we can have a first example, which is going to be classical theory. So, what would you say is a classical theory? Yes?
If we know, for instance, all the oh no, English, I'm sorry. If we know all the starting points, all the velocities and stuff, we can predict the entire movement of the things. For instance, if we knew all the start, the initial
yes.
everything, I was missing the word, I'm sorry, then we can predict everything entirely.
Yes. There is a slight problem with that, that if you know the initial state of a quantum system, then based on Schrödinger equation or Limbaladi equation, you can also predict the state at a later time.
Like, know something for sure and not have like just I'm sorry, English.
No, it's fine, it's fine. Yes, but then there's also a problem, because I can take this pen, which we all would agree is classical, right? I can now do this thing where I say, like, in which hand is the pen? Like, you see me, you have all of the information about me, but yet there is some kind of probability for you.
Yeah.
But yes, it's somehow your intuition is going in the correct way.
If we would describe something in a classical manner, then to knowing the initial conditions, we might predict the evolution of the system in a not specifically discrete manner. On the other hand, we might describe the system in a way that, due to a specific initial condition, it only results in one particular solution. So, knowing all initial conditions, we do not have to solve it statistically, or giving a probability of the evolution of the system.
So, am I understanding correct that your argument is that classical theory, that you would call a theory classical if the outcomes of the theory are always deterministic? So there's like a specific.
But knowing the initial conditions, we might describe a system which would lead to specific measurements that are compared to a quantum theory that would be, for example, if we describe an evolution of a particle more due to a cloud of probability, where we could measure this particle. In a classical theory, it might be akin to something like a line, where it's more determined where we should find something.
Well, yes, but also in quantum theory, you can always take the movement equations and just apply them to the measurement device in the Heisenberg picture, and then you somehow, involve them in the inverse direction of time, and you can find a state that gives you the measurement outcomes you would want. So somehow you can always engineer quantum systems in this way as well, as long as a state with specified measurement outcomes exists, but this can be also a problem in classical theory. So here's the thing. Your intuition is correct, and the best way, or somehow the best way known to me to put it into a solid ground, is that we have to realize that there are two different ways to access systems, or somehow systems in a lab. We can either be told that the system is described by, say in a quantum case, by wave function psi, which is equal to something, something, something. I can here give you some correct example and some normalization factor, and you know what that is. Or I can tell you, and I can give you something and say like, here's the quantum system, do with it what you want. And these things are essentially two very different things in quantum theory, because if I tell you the wave function, you can in fact predict outcomes of all of the measurements. If I give you the one instance of a quantum state and say it's in some kind of wave function, I don't know what it is, go and measure it and do something with it, you cannot predict the outcomes of all measurements because you can only measure it once, and after you measure it, the system is disturbed, gone, and you cannot measure all of the other things. Okay? Does that make sense? So it's something different knowing the wave function, having it written on paper, and just being given like, here's a quantum system. But classical theory is the unique theory where these two things coincide. So if I give you a classical system, the important thing is that you can actually, in principle, measure and write down the position and momenta of all of the particles. Sure, there can be like a lot of gas molecules in here, but in principle, you can do it. In quantum theory, you cannot do it even in principle. So we will be mostly looking into finite dimensional systems because we want to use them for information processing tasks, hence, which is very good because then all of the math becomes simpler. But then we can define classical theory as follows: that the set of states will be given as the convex closure of some states Si, such that these states are perfectly distinguishable. Okay, which means that if we have that there exists a measurement M which takes in a state Si and maps it to the label I. And this means perfectly distinguishable because what this does is that it takes the system in this abstract kind of sense where you interact with it as with a physical system, and it gives you back the exact label. Okay. So somehow you should see this as an analog of what would be in quantum theory measurement of wave function, except for you cannot measure the wave function in quantum theory. And this convex hull just means that we take these points and then do all possible convex combinations of them. Because as we argued, there should be a convex structure of the state space. Now, the measurements. So we have this one measurement M. And then what we take is that we take all possible coarse grainings, where we say that, well, instead of outputting the label I can output the say 0 if the label is odd and 1 if the label is even, or some kind of, I can somehow merge the outcomes together. So I don't have to output this exact information. I can somehow decrease the amount of information I give you about the label, and plus, also, there's some kind of probabilistic post-processings. These thick mixtures. And the transformations. So these are, in general, permutations of these points in the easiest sense. So the transformations can be seen as permutations. There can be also coarse grainings. And in general, we can model the transformations by stochastic matrices. Which just says that if I give you somehow a system in perfectly pure state that you can distinguish, I can always make it more noisy and add some random noise, shake it a little bit, and somehow destroy the information that's there. So do you agree that this is a classical system? This is what we should consider classical systems? Or are there any objections? Or where do we use classical systems?
They're just easier.
So, what?
They're just easier.
No, but in everyday life, where do you use them?
Where?
Yes.
Everywhere.
Yes, exactly.
Just where they predict the real observable outcomes.
Yes. But in the finite dimensional case, a specific example would be computers, right? So a simplest computer would have 1 bit, which means it would have 2 states. There would be something like state S0, which would represent the bit having value 0, and there would be state S1, which would represent the bit having value 1. Okay? And we can see these two as a point on the line, where here in the middle we have the convex combinations. This measurement M is just something, it's something like a readout, which gives you the value of the bit. It's always deterministic because it always just, somehow if I give you a random bit in some kind of state, you can always look at it without destroying the information and read out the value of the bit. Of course, we have the convex combinations, and then we have the transformations, which in this case it's identity, it's a knot, which somehow switches them, but then you can have also probabilistic transformations. For example, when you map this point here, and you map this point here, which would be a probabilistic transformation because you are mapping the perfectly distinguishable states into some kind of states in the middle of the line which are not perfectly distinguishable anymore. Of course, we can then say that, well, we can have something like 2 bits, which would be represented by a tetrahedron. And the reason why these points have to be linearly independent is so that there exists some kind of measurement that would exactly distinguish them. Are there any objections, or is it okay if I call this classical system? Very well. So now I would want to introduce quantum systems as an example, but for that I have to review all of the mathematics because somehow I was told I should not really trust what you do know or do not know. I will try to be a little bit fast. Feel free to stop me at any time. I can explain anything a bit more in depth. Sometimes I'll just state that something can be proved or shown based on the information I've provided you with before. In this case, it's I would somehow recommend trying to do that at home. But of course you don't have to. But it could be a good exercise. But it's up to you. So how many of you had something to do with complex numbers before? Good, almost everyone. So you can, now in this part, you can always tell me to either speed up or slow down. And if you tell me to slow down, I'll slow down, and the people that would like me to speed up would have to wait a little bit, because what I'm going to tell you now is going to be the mathematical foundations of what we are going to be doing the whole semester. So if you somehow get lost now, you're not going to find yourself much more later, you know? So this is like also the only part that I would somehow recommend you review properly before the next lecture, okay? So mathematical language of quantum information. So as I said, the first important things are the complex numbers, denoted C, and the complex number is something like x plus ya. And if we have a complex conjugate, do you use star or bar?
Depends.
On what?
Star, some use bar. Your choice.
I think in where I come from, it's star for physicists, bar for mathematicians. Is it the same here? Okay. And of course, then we have something like z times w, which is x plus yi, a plus ib. It's ax minus by plus I, ay plus bx. Good. Now we need to define a Hilbert space. Do you know these things from standard quantum theory? Actually, do also Dirac notation at standard quantum theory? Okay, so most know this, everybody knows this? Is it most or everyone? Okay, so I'll be very fast about this. Hilbert space here will be using only finite dimensional. So it's usually going to be denoted H, and you can think of it as something like a columns in complex numbers. There's going to be a standard computational basis, which is going to be, which you can imagine something like this. And then there's 2, and so on. And every vector can, of course, be written as a linear combination in this basis. So far, everybody's seen this before, right? Good. The inner product is something like bi bar alpha I, where phi is given as sum over I, bi I. So we are doing inner product, which is antilinear in the first window and linear in the second window. So the physics way, not the math way. Just to confuse, just to be more confusing. The norm, of course. And we usually care about normalized vectors, so vectors with norm 1, because of normalization of probabilities. Now, something that's usually not covered in standard quantum theory is the tensor product. So if we take two vector spaces, two Hilbert spaces, H and K, then we can form the tensor product of the two Hilbert spaces, which is just Hilbert space spanned by, so this is just spanned by product basis, which is something like Ij, which is just a shorthand for I tensor J. So if I have two Hilbert spaces, I can just fix the computational basis, and I can now define a new Hilbert space spanned by these bases, where you should see these as some kind of fancy notation. Of course, then you can show that the tensor product is linear in both components. So if you have something like alpha psi 1 plus beta psi 2 tensor phi, then this is nothing else than alpha psi 1 tensor phi plus beta psi 2 tensor phi. This is, okay. Yes, a big note is that in general, Ij is not equal to Ji, and psi tensor phi is not equal to phi tensor psi. In other words, tensor product is not a symmetric operation or antisymmetric operation, it's just an operation. It's just some kind of product. Okay. So now we can define operators. And an operator A is going to be nothing else than a linear map from a Hilbert space to a Hilbert space. So linear, of course, means that A of alpha psi plus phi is equal to alpha A psi plus phi. You can somehow persuade yourself that you only need to check for these kind of things, and if you would have general coefficients that's doing these things twice, and so on. And there's a special class of operations, a special class of operators that we usually denote like this, as a cat brass, where psi 1 and psi 2 are vectors from the Hilbert space. And what they do is that if you somehow act with them on a vector phi, what you get is psi 2 phi, psi 1. So you should treat this completely as some kind of graphical calculus. Just smoosh the two things together, you get an inner product, so you can move it as a number forward, and you get a vector over here. Okay. Now we can denote the very special operator, this one, which we can define as a sum over computational basis. What's this operator? What does it do? Yes, exactly. And you can prove that identity on psi is equal to psi. How does one prove that? Yes?
You could write psi in the I basis.
Yes. And what's this? Yes. Everybody knows this notation? Okay. What does it mean for two operators to be equal to each other? Yes?
They've got the same output for all possible inputs.
Yes. So if we have operators A and B, we say that A is equal to B, if and only if A psi is equal to B psi for all psi in H. Actually, what does it mean for two vectors in Hilbert space to be equal to each other? So they have the same output, so you should know what this equality means between vectors. Yes?
They should have the same coefficients represented in the same basis.
Yes, yes, very good. Or we can say that psi1 is equal to psi2 if and only if phi psi1 is equal to phi psi2 for all phi. If their inner product with any other vectors are always the same. From which somehow we can derive this, because you can see the coefficients as inner products with the computational basis. Okay? Of course, given two operators, we can form a sum of operators, which just acts on a vector by summing the outputs. We can form an operator which is a multiple of an operator. Well, which means that operators form what? Yes?
A vector space.
So I know there's few mathematicians. Are you one of the mathematicians?
Certainly.
Okay, yes, operators form a vector space. How do we define the matrix of an operator? So you had linear algebra, you should know how to do matrices of, yeah?
With the basis, we can sandwich the operators. The basis just gives us the entries for matrix representation.
Yes. So I'll now show you the way I actually remember and derive this like every other month when I need this result. And I do it as follows. Of course, you're free to remember this any other way. I just find this very useful, because it's somehow very minimal on the stuff you have to remember. So if I have an A, then I can write this as identity times A times identity. Oh, by the way, I never defined the product of operators. How does one define that?
It's the consecutive execution.
Yes, exactly. Composition. Yes, consecutive or composition of maps when you see them as linear maps. So this is meaningful. Is this correct? So now we can denote this as Aij, and we can call it the matrix of an operator or component of the matrix. And you can realize that these are operators that somehow take the jth element of a basis and map it to ith element. So it's something like a matrix which is 0 everywhere except for one place where it's exactly equal to 1. So then when you sum this together, you get the matrix. And I'm showing you this because this is for me the most useful way to remember this thing, but you're free to do that any other way you like. And from this you can actually verify that if you have A times B, then this can be given as sum over ijk, aik, bkj, ij. And how would you think you verify this? Like, this is the product of operators, this is the product of matrices. One would assume that they are the same thing. But how would you prove this? Yes?
You could take the representation in the line above, do this for the second operator as well. Then you've got two more indices, k and l, and then the two of them will sandwich and produce a Dirac delta.
Yes, exactly. Or you can simply go identity times A times identity times B times identity, and you get here, which is the same thing. Very good. Adjoint operators. Do you know how to so in quantum theory you must have heard that the Hamiltonian should be self-adjoint. So how does one define adjoint operator, Tion operator?
We need a scalar product.
Yes, but how?
We can pull it to the other side.
Yes. So given operator A, we can now define psi, phi A star psi to be equal to psi A phi bar. Now, the one thing that I never mentioned, but you probably know, is that here we have that phi psi is equal to psi phi bar, so it's a sesquilinear form. I believe that's the name. And so what this just means is that we are applying the A here, and here we have psi. So we're applying the A to the first vector in the inner product, not to the second vector in the inner product. But this notation looks kind of awkward, so it's easier to write it this way. Now somehow I claim that this uniquely defines an operator A star. Is that true? Yes, because if you know this, then you know how A star acts on every psi, and from that you can reconstruct the linear map. Somehow this is in infinite-dimensional Hilbert spaces, it would be a bit deeper result, because here we would be defining something like a bilinear form, and then from that we define the operator. Very good. How does this work in terms of matrices? What's a matrix of a joint operator?
The complex transpose of the
Yes. So the Hermitian conjugate or conjugate transpose. Okay, so some operators are going to be self-adjoint, which means that they're equal to their adjoint. In which case, this is the same as saying that the operator A can be written as a sum over eigenvalues. Or we should probably know this psi I. Where these on the i's are in R. So this is usually called the spectral theorem, which tells you that you can decompose the operator into some kind of these ket-bras or projectors and eigenvalues. And we know that every self-adjoint operator can be decomposed like this. And on the other hand, every operator of this form must be self-adjoint, because somehow the adjoint of this thing is itself, and you would just do a complex conjugate of a real number, so which is itself again. Then we can also define positive semi-definite operators. So we say that A is positive semi-definite if A is self-adjoint, and if we have that A is sum over, can be expressed in this way, such that all of these eigenvalues are positive. Okay, so positive semi-definite operator is just an operator which has only positive eigenvalues, which is the same thing as saying that psi is positive for all psi. Somehow we can see that if there would be a negative eigenvalue, I can just sandwich with the respective eigenvector and get something negative. So this implies all eigenvalues are positive. And on the other hand, if all eigenvalues are positive, you can directly prove that this kind of number is always positive. And how do you prove that this number is real? Because you know there's no inequality in complex numbers. Yes?
If you know that the operator is self-adjoint, you can just adjoin the expression you have written there, and then you can see that lambda I conjugated must be the same as lambda.
Yes, you can show that this number is equal to its complex conjugate by using this result and the definition around here. Very good. Trace of an operator. Actually, do you say trace or Spur? I think all German books should say Spur.
Trace is fine.
No, but how do they teach you? You know, like.
Well, in German, it's
Yeah.
Spur. That's right.
Yes.
Yeah, in English it's trace.
Yes. So it's just sum of the over the all eigenvalues, which is the same as sum over I, and you can actually prove that those two sums are always the same as long as this is orthonormal basis. And an important property is that if you trace A times B, then that's the same as trace of B times A. So it's somehow cyclically symmetric, the trace. Fine. Unitary operators. So given two orthonormal bases, so a basis is orthonormal if all of the vectors have norm 1 and are orthogonal to each other, so their inner products are 0. And if we have two orthonormal bases, so O and B's, which is psi I and phi I, we can define the operator U, which will be given as sum over I, psi I, phi I. And what this does is that it maps one of the bases to the other. And then one can show that U times U star is equal to U star U is equal to identity, which you get immediately because if you somehow apply the star here, what you're doing is that you are switching these two things. So somehow you can see that psi, phi, and this star is phi psi. So if you apply the star here, you switch all of these two things, and once you do this, you get the identity decomposed in a specific basis. And then this argument that all of the traces are in every orthonormal basis the same can be just written as U star is equal to trace A. Do you see how this implies that the trace is independent of the choice of basis? Because I can always just plug the U's here and get a different basis from that here. And how to prove this formula is just by taking this U and putting it here, which just uses this cyclic property. Very well. So now this is all of the math we'll need for all of the semester. I'm very happy we got through it and we don't really have to spend much more time with it. Are there any questions about the mathematical aspects? Was this too boring, too known, too new? Okay. So now we want to define quantum theory as another example of such kind of theory that describes experiments as we did for classical theory. And this is rather straightforward. What we do is that we say that the states of our theory are nothing else than density matrices. And rho is a density matrix, so this can be usually denoted D of H. And this is a set of matrices, rho, or linear operators on the Hilbert space, such that they are self-adjoint, positive semi-definite, and their trace is equal to 1. Now this, have you seen this before? Also that thing. Now I'm really surprised because like this is usually not taught at standard quantum mechanics lectures. Okay, then measurements are given by P of EMs, which is nothing else than a set of operators, MA, labeled by A, so this A usually runs from 1 to n, such that all of these operators are positive definite and sum up to identity. Transformations. Some transformations are of the form rho gets mapped to u rho u star, which we would call a unitary transformation. But in general, the transformations are given by what we call CPTP maps, so completely positive trace preserving maps. Now, this completely positive means that they behave well on entangled states. What are those? That's going to be the subject of next lecture. This trace preserving just means that if we apply the map in a Heisenberg picture on identity, we get again identity. Or this just means that phi of rho and trace is equal to, or phi of x is equal to trace of x. Now, do you know how this corresponds to the standard quantum theory that people are taught like in usual courses? Yes?
The traces like to do with the sum of the diagonals of the density matrix, and these diagonals represent the probabilities of certain, or linked to the probability of certain measurement outcomes. So this is essentially a condition to say that like the probabilities of all of the possible measurement outcomes should add up to 1, because otherwise it would keep them.
This one, yes. And this one as well. Oh, this one says that the probability should add up to 1, and this one says that transformations should not break that.
Yeah.
Yes. Yeah, but I mean, like, if you would take someone who just did harmonic oscillator and hydrogen atom in standard quantum theory, how would you explain this to them? Do you know how to do that step? Yeah.
I mean, you usually learn it with just pure states.
Yeah.
And the density matrix is a generalization of that. So usually, if you just have a pure state, you can write it as a Cat-Bra.
Yeah. Okay, good. Good. So
Generalize it.
So you know considerably more than I actually assumed you would. Yes. Oh, what I never told you is that if we want to, in quantum theory, compute the prediction of this experiment, what we do is that the probability of observing outcome A is given as trace of the transformation acting on rho, and here MA. Now, in most important cases, the transformation will be identity, in which case this is just the trace of these two matrices or operators. Good.
Sorry?
Yes?
You wrote down the star of 1 is 1, but isn't that unitality and not completely positivity?
Yes, that's the trace preserving part.
Okay.
Yes, that's unitality.
Yeah.
You really do know way more than I expected. So for the sake of completeness, in standard quantum theory, a state would be given by a vector in a Hilbert space, which is normalized, so the norm is equal to 1. And then what we usually do is that we want to compute mean values and probability distributions. So given an observable A, we can decompose it as a sum over A, and here we have phi I. And then what we can do is that we can say that the probability of, if we measure this observable, of observing the outcome I corresponding to the, or of observing the value AI is just giving us this inner product, phi I psi. And the mean value of A is given as sum over I, AI, P of AI. This is usually how we compute mean values, just by averaging over all possible values. Now here the thing is that if we have this, we can write it as phi I psi squared phi I, which is nothing else than the trace of psi times phi I. So this thing is our density matrix, and this is our POVM element. Now what's going on is that the density matrix, they don't have to be of this form. We usually call this as a projector or pure state. They can be, a general density matrix is going to be something like a sum over probabilities, or maybe I should call them QIs, and there's going to be something like psi I. You can prove this using the definition of a density matrix. Why we want this is that because we want to somehow allow for states which are not perfectly pure states, and this will happen because when we have, for example, some state of several particles, they can be entangled, or there can be an environment that's present in our experiment. And now if we would want to work with pure states, we would also have to include environment in the pure state. But this is rather problematic because then we would have to prove everything that for all possible environments that we don't know what they are, this is the result of the experiment. And it's easier to actually use the density matrix as an effective description of a system where there is an unknown environment that's out of our reach, and we just somehow, because of the unknown environment, we don't have complete information of about our state, because some of the information about the state is stored in the environment. Is that roughly clear? Okay. The same thing goes here with measurements, because not all POVMs are of this form. And what can happen is that these are called projective value measures, or PVMs. POVMs are more general. What's going on here is that we can have a noisy measurement, so we can have measurements where some external noise is added, our system is shaking, there are some thermal fluctuations, which somehow changes the effective form of this operator. We also can have convex combinations of these types of things as per our assumptions, so we have to work with those general things. And the same goes for transformations. In principle, we should consider only unitary transformations, but then if you look only at what part of your system is doing, and you are not considering the unitary transformation that also includes unknown environment, you get some kind of effective transformations. But then again, we will not care about the transformation for most of the transformations, so we don't have to worry that much about that. So that's how you go from standard quantum theory to this kind of definition, or this kind of description that's used in quantum information. Is that clear? Have you already seen this like 5 times?
Maybe 1 or 2.
Okay, good. Was it clear the first time, or does it help to see it again and again?
It helps to see it.
Very good. One more thing that's extremely useful is to define a purity of state. Now, this is gamma of rho, and it's called the purity of state. And one can now prove that gamma of rho is equal to 1 if and only if rho is pure state. Now, this is a often useful result, because if I give you a density matrix and tell you and ask you to give me a properties of this density matrix, checking purity is one of the simple ways to determine whether the state is pure, and if the state is pure, usually investigating its properties is way simpler than for a proper density matrix. Actually, for pure states, most of the things are rather straightforward and obvious. And in general, you can prove that the purity of a state is less than 1, so the extreme case are pure states, and it should be more than the 1 over dimension. Where dim H is the dimension of the Hilbert space. Good, now we know everything and we can start with entanglement, and that's going to be the order of next lecture.